I've used a piece of code, the read switch timer part, from this project on some of my projects for many years now, and it's proved to be very reliable. I've used it most on the automatic shifter for my bicycle, measures wheel RPM and cadence. On a bicycle power meter it measures cadence, also on a cliff railway to measure its speed from a brake disc, and more recently on a wind turbine data logger to measure wind speed and turbine RPM. Now, a lot of people have said, well, why don't you use a Hall effect sensor? Well, reed switches come with a very handy bracket designed to mount on a bike frame. They are weatherproofed and so far have proved to be very reliable. Now, anyone who has tried this code will know there is one minor issue with it, and that is if the magnet stops next to the reed switch, it will give the maximum output. Before I reveal my improvement for this code, I'm going to go into how it actually works, so as you might be able to understand a little better what I've done to improve it. Now, my improvement gets the RPM up to around 1,600, so that's equivalent to measuring around about 120 miles per hour on a bike, so it's more than adequate for a cycle computer and more useful for other things. So these are the main values that are important for the running of the code. So we take here the status of the reed switch and store it, and the timer, it's obvious what that does, and then these two which are used for the debouncing. Now you could do away with this and just write 100 in the code further down, but it helps to have it stored up here so you can change it easier. And this here is the output. Now in the setup we set the read counter to its maximum value, and you'll see that's important later. And this here is the setup of the timer interrupt, which I'm not going to go into, but you can set it onto timer 2 if you want to. And here we have the main code, which will operate at 1,000 times per second, the way the timer is currently set up at 1 kilohertz. First we read the status of the switch and put it into this value here, and then we have this piece of code which we want to operate once per rotation and only once. And that's the point of this part of the code here, to try and prevent it from triggering twice or more times. Because what happens in this piece of code is here we calculate the output, and so that's taken from the timer and we divide a value by it. Now this value could be anything that you want to get the right output. You can see I've got different values here for like meters per second, miles per hour, and so on. Here we have the timer set to 0, and the read counter is set to its maximum value. What happens in these next two bits of code is to do with the debouncing and this read counter. Now this piece of code here will operate and decrement the read counter once the switch is closed, and this one will operate it when it's open. It will decrement the read counter when the switch is open. And then that of course means that until that's decremented, this piece of code here can't operate because it has to be 0. Here we have the timer. If it's too high a value, we just say that the rotation has stopped, and so we set our output to 0. And this one here, it operates on every time through this code, and it just increments the timer, and then obviously it gets reset in this piece of code here. Now to explain this a little bit more clearly, I'm going to show you the serial plotter so you can see what's actually happening as the code is operating. To do that, I'm going to output obviously the timer and the read counter. When I open the serial plotter, the Arduino will be reset and then it will start outputting the data. So what you can see here is the red line is the timer, and that's counted up to its maximum value. Down here in green, which you can just about see, is the read counter, which was set to its maximum value on startup of around about 100, and is now counted down to 0. And the output will be in blue. So when I start spinning the wheel, we can see that on every rotation the timer is reset, the read counter is doing its countdown, and the output is being updated on every rotation. Now if I speed the wheel up, you will see the limitations in maximum speed of this code. At that point there, the time per rotation is less than the read counter value, maximum read counter value, and so it's missing every other rotation, so the RPM drops by half. What I'm going to do now is put the magnet in front of the switch, and you can see what happens. And there we have it continuously looping round, so that the read counter value is pretty much setting what the timer value will be, and we're just getting the maximum output, which I think is around 590 RPM, something like that. What I have worked out to fix this code is to remove this whole section here. And so what that means is that this read counter will only decrement once the switch is open, so it prevents that loop from being set up where this just keeps, when the switch is closed and the magnet is sitting in front of the switch and it's staying closed, this read counter just keeps decrementing, and then this bit of code here keeps re-triggering, and what you end up with is the shortest timer value, which is equal to this maximum read counter value, and so you just end up with maximum output. So if we get rid of this piece of code here, the read counter will now only decrement once the switch has reopened after the magnet has moved away. That also means we can reduce this value here quite dramatically, and I've found that actually you can drop that down to 1 and it still works. It really just acts as like a latch, I suppose you'd call it, just to prevent this from re-triggering again immediately. So effectively this switch has to reopen. Well, it effectively gives it one chance at bouncing, and it prevents it for once. So it makes sense to, I've left it at something like 10. But I've found that really, because we're sampling the switch at a rate of 1 kilohertz, 1,000 times a second, which is really quite slow actually by microcontroller standards, you can get a lot of bouncing can go on in between samples and it just completely misses it. So debouncing really at this 1 kilohertz rate is not that critical. So I would say really you could probably put this maximum read counter to something around about 5 would be more than adequate. I've tried with the switch just slowly switching it on with the magnet, and it's never been less than this value that I put in here, so, which says that so far I've not managed to make it bounce when the switch is going on. So that's the fix for the code, and now I shall show you on the serial plotter what effect it has. I'm using my bicycle wheel for testing, and because I can't make it spin at more than about 800 RPM, I've installed 3 magnets on it. They're not equally spaced, which is why it's fluctuating. So the RPM on here, you have to divide it by 3 to get the real RPM. I can now demonstrate though that it could, if there was one magnet on it, spin at reliably up to around 1,500 RPM. It's just over 1,500. See, because of the error in the position of the magnets, there's quite a lot of fluctuation on it. But if it was one magnet, that would be much smoother. And there it starts to drop out. So what happens now when I move the magnet in front of the switch? Well, you can see that worst case is that the output will go to its minimum recordable RPM, which is actually determined by the maximum allowable timer value. I think it's currently at the moment with a timer value maximum of 2 seconds, 2000. It's at around about 30 RPM is the absolute minimum you can read. So if you set the maximum timer value to more than that, the minimum RPM recordable will be much less. And now if I move the magnet away, you can see just at the very bottom of the screen, the green line is the maximum read counter value of 10, and that decrements down to 0 again. So that sums up this video. Thank you for watching.